Check it out now, y'all.
nanoHUB-U, online instruction.
Okay, welcome back. Let's continue our discussion about MOS electrostatics. So what we talked about in the last lecture was the type of MOS structure that has been most common up until today or current day technology, but more and more people are looking at a slightly different technology for MOS in the future. So we'll be talking about a particular structure called extremely thin SOI, and this will give us an example to see what happens in a different physical structure, but it'll also give us an example, an opportunity to make some points that are more general. So we've been talking about a bulk MOSFET, and what I mean by bulk is that it's built on a piece of bulk silicon. For our purposes, this silicon wafer is considered to be infinitely thick. You know, real 12-inch wafers are about 775 micrometers thick, but you know, you'll recall when we computed depletion layer thicknesses, they were on the order of 25 nanometers or so. So these wafers are very thick. We can consider that there is no band bending deep in the bulk, and we can use that as a reference for the potential and set the electrostatic potential to be zero there. This is what we mean by a bulk MOSFET. Now let's take a look at a different type of MOSFET. This is a silicon on insulator MOSFET. So in this case, the cartoon here shows you that the device itself is built on a silicon wafer. That's the substrate. And then there is a bottom oxide that isolates the transistor itself from the silicon substrate. So the silicon substrate is just a platform that we used to hold everything while we do the fabrication and processing. And then the actual device is built on a very thin layer of silicon on this insulator, SOI. And if you look at a TEM from an extremely thin SOI device produced at IBM, you can see that thin insulator right under the gate electrode here. And these days, that insulator thickness is on the order of 10 nanometers or even thinner. So this is a regime that is completely different from the bulk. The electric fields will penetrate all the way through this thin silicon layer, and the electrostatics will be affected. So the goal of this lecture is to try to understand how MOS electrostatics plays out in a structure like this. Okay, so let's go back to the bulk for a minute. These are the kinds of energy band diagrams that we were talking about when we go deep into the bulk silicon. It's just a p-type silicon wafer and the bands are flat. Near the surface, we apply a positive gate voltage, increase the electrostatic potential in the semiconductor, and pull the bands down. And the electrons then, when we invert, pile up at the surface. Now, if that potential well that we've created by the gate voltage is thin enough, then the electrons are quantum mechanically confined, and we would call this a quantum well. Well, how do we decide whether that's the case or not? Well, what's important is whether the potential energy varies on the scale of the electron wavelength, or the de Broglie wavelength. And the de Broglie wavelength is something that we can easily estimate at room temperature, putting in a typical value for an effective mass. And if I use numbers for silicon at room temperature, the de Broglie wavelength of thermal average electron turns out to be about 6 nanometers. Well, these inversion layers are 10 nanometers or less in thickness. So we really are in a region where we should think of these electrons as quantum mechanical particles. So in a bulk MOSFET, this potential well is created by electrostatics. In an extremely thin SOI structure, the potential well is the extremely thin silicon layer itself, and the oxide layers on the top and the bottom are very high potential energy barriers that confine electrons in that physical structure. So in both cases, we have a potential well, we just have different shapes of potential wells. All right, so let's look at a very simple potential well. It's a textbook quantum mechanics problem, particle in a box. Let's think about TSI as being the thickness of this very thin silicon layer. Let's think about the oxides on both sides as being infinite energy barriers. Bottom of the conduction band is down here. We'll just set that equal to 0. And what we have is a classic textbook particle in a box problem. So you'll remember the Schrödinger equation, where this parameter k squared relates the energy with reference to the potential energy to the value k squared. The solutions to this equation are sines and cosines. Only the sine will satisfy the boundary condition. If I put y equals 0, then sine is 0, and the wave function has to go to 0 because there's an infinite potential well that's preventing it from going out. In order to satisfy the boundary condition at the other side, this parameter k has to be quantized in units of pi over TSI. So n is an integer, 1, 2, 3, 4, 5. If we relate now this quantized wave vector to the energy, we'll find these quantized energy levels. And we'll get a set of quantized energy levels that satisfy those boundary conditions. And I'm labeling those epsilon 1, epsilon 2. They just correspond to n equals 1, n equals 2, whatever. So you'll notice that if you have a very light effective mass, these quantized states are very far above the bottom of the conduction band. If you have a very thin quantum well, same thing happens. The quantized energy states get pushed up far above the bottom of the conduction band. Now, we'll have a Fermi level somewhere, and that means the states, the subbands below that Fermi level will be occupied. Some bands above it will be mostly empty. So we could have one or more subbands occupied depending on where the Fermi level is. Now, it's important to note that we're drawing an energy band diagram in the direction of confinement, normal to the channel in an SOI structure. In the YZ plane, normal to the sheet here, electrons are free to move. So they look just like propagating plane waves normal to the plane, but they're not free to move in the direction of confinement. Okay, so now let's see if we can figure out what the electron density would be in this quantum well. If these were classical 3D electrons, we would just take our usual relation between the electron density per cubic centimeter and the location of the Fermi level. It's related to that Fermi-Dirac integral, and this effective density of states, which includes things like effective mass and temperature. And this expression would say that the electron density is uniform within the quantum well. But for a quantum mechanical particle, that's not going to be the case. The electron density is proportional to psi star psi, where psi is the wave function. That wave function had a sign behavior, so the electron density is proportional to sine squared y. So it must go to 0 at the two boundaries, and it's peaked in the middle. So quite different from the classical 3D unconfined case. Now for a MOSFET, we're interested in the total number of electrons per square centimeter. So we integrate throughout the thickness of the structure, and we'll get the sheet carrier density n per square centimeter. Now, the easiest way to do that is simply to integrate the two-dimensional density of states times the probability that each state is occupied by Fermi function, and perform that integral. And if we perform that integral, we need the density of states. It's just a step function that's 0 below the first confined energy, and then steps up to a value given by the 2D density of states. So you do that integral, this is the answer that you get. So we get an analytical answer, but actually this logarithmic term here is the Fermi-Dirac integral of order 0. So that particular one has an analytical expression, and you can see now that what matters is not the difference between the conduction band energy, or the Fermi level and the conduction band energy, but the difference between the Fermi level and the first confined state. This will give us the number of electrons in the first state. If I is equal to 1, if I is equal to 2, it would be the number of electrons per square centimeter in the second state, and we would just have to add up all of the subbands that are occupied. Okay, quantum wells can have different shapes. For example, we might have a triangular quantum well. If we have a triangular quantum well, we'd have to solve a different differential equation, but we would still find a set of quantized energy levels. They would be given by this expression. So the shape of the quantum well determines the specific values of the subband energies, but if I want to compute the electron densities, I'll use the same expression that we just developed. I'll just use the appropriate quantized energy levels. So same expression, but different energy levels. Okay, now this quantum confinement can have a very measurable and important effect on devices. So you can, if I look at a very thin device, and if I think about what the threshold voltage will be, when you measure the threshold voltage, you'll see that the thinner the structure gets, the higher the threshold voltage is. And that's easy to understand, because what quantum confinement does is basically push the bottom of the conduction band up in energy, which means we need a larger voltage to pull the bottom of the conduction band down near the Fermi level and populate it with electrons. So that shift is just due to quantum confinement, and it can be sizable enough that people worry a lot about this in devices these days. Now, another detail that we're not going to discuss really much at all in this course, but I just want to alert you to the fact that we have complicated band structures in some semiconductors. For example, you might recall that in silicon, the constant energy surfaces are 6 ellipsoids pointing along the x, y, and z axes. Now, if I ask which effective mass to use here, remember I have a longitudinal effective mass and a transverse effective mass, so it's not so clear which effective mass to use. Well, the one you use depends on the direction. If the direction of confinement is in the y direction, then the electrons will respond with the longitudinal effective mass, and I'll have a set of energy levels corresponding to those 2 blue ellipsoids. But I've got 4 other ellipsoids, and they have an effective mass in the y direction that's the lighter transverse effective mass. So I would use a lighter mass. The first subband for those 4 valleys would be higher in energy than the first subband for the blue valleys, just because of the difference in effective masses. So some of these details of band structure will be important when you get to actual implementations of devices. We're mainly going to be focusing on general overall concepts here, so we won't get into these kinds of details in this course. Okay, so how does all of this work in practice? Well, it works by solving the Schrödinger equation self-consistently with the Poisson equation. So what we do is we, first of all, solve the Poisson equation if we have a guess for how the potential energy varies with position. Maybe it's this simple rectangular quantum well. Once we do that, we know the wave function, we know psi star psi, now we know what the electron density is. The second part of the process then is to put that new electron density into the Poisson equation, solve the Poisson equation, get an electrostatic potential. The electrostatic potential influences the conduction band profile. Now I have a new guess for the conduction band profile. We'll take that new guess, we'll put it into the Schrödinger equation, solve for the wave function again, and just repeat the whole process until it self-consistently iterates to a solution. So that's what's done in practice to determine these energy levels and the shape of the quantum wells. We're going to avoid that, but I can show you what some of the results look like from a tool that's available on nanoHUB. This is a very thick SOI structure starting at 250 nanometers. Here's the oxide on the bottom, here's the oxide on the top. You can see that there's some band bending inside this structure. As we go to thinner and thinner silicon layers, the bands get flatter and flatter. The one that we're going to be looking at have thicknesses of 10 nanometers or less, so we can just consider that to be a flat quantum well where we have simple analytical solutions. If you look at the electron densities that were computed from that simulation, you can see that for the thick wells, we have inversion layers building up at the top and the bottom. Just looks like 2 bulk MOSFETs with an inversion layer at the top and an inversion layer at the bottom. But as you get thinner and thinner, you can see that you can start to see the sine squared Y spatial dependence, and there's an electron profile that just looks much different than it does in the bulk. Okay, so that was very quick, and I just wanted to make a few points and sensitize you to the fact of what quantum wells are and what determines their shape. The key point is that these electrons are quantum mechanically confined, and we should include that in our analysis. Okay, so what's the point of this lecture? What we would like to do is what we did in the previous lecture. Develop a relation that gives us the inversion layer charge as a function of gate to source voltage, but to do it for this extremely thin SOI layer and compare the results to what we got in the bulk. To make things simple, I'm going to assume that the structure is symmetrical. It's got the same thickness oxide on the top and the same on the bottom. We apply the same gate voltage on the top and the bottom. We'll call that a double gate geometry. So here's our structure. Very thin silicon layer, oxide on the top, oxide on the bottom, same voltage applied to the top and the bottom. Okay, I'm going to assume that this is an undoped structure, or that the doping is very, very light, and we're going to be drawing energy band diagrams normal to the surface, just the way we did for the bulk MOSFET. Okay, so let's take a look at what these energy band diagrams would look like. So here's my conduction band, here's my infinite barrier due to the oxide, here's my valence band. If I've adjusted my work functions properly or appropriately, I can position the Fermi level to be more or less in the middle of the band gap for zero applied gate voltage. You just do that with work functions. All right, so we have these confined states. We have a set of them in the conduction band. We have a set for holes in the valence band. The actual band gap now is the difference between the lowest energy in the conduction band and the highest energy in the valence band. So this quantum confinement has effectively increased the band gap. You know, people see that when they do things like make quantum dots and look at the color of the light that comes out when they're photoexcited. They depend on the size of the quantum dot because of this quantum confinement effect. Okay, now if I want to compute carrier densities, I'll just use my expressions with the 2D effective density of states and the Fermi-Dirac integral. And what's important is where the Fermi level is located with respect to these subbands that are epsilon sub 1 above the bottom of the conduction band, epsilon 2 depending on which subband I'm looking at. For this lecture, again, I'm going to assume Boltzmann statistics, so the Fermi-Dirac integrals become exponentials. That just makes it easier to do the algebra and the bookkeeping. We can illustrate the concepts that way. In practice, we'll have to do things a little more carefully and use Fermi-Dirac integrals. Okay, so what would things look like for various potentials? So if this is my starting point, I'll just call that my arbitrary reference. That's zero potential in the semiconductor. Psi sub s now refers to the semiconductor potential, which is uniform across that. If I apply a positive gate voltage, I'll induce a positive potential in the semiconductor. That'll lower the bands down and put more electrons in the first subband of the conduction band. If I apply a negative gate voltage, that'll make the surface potential negative. That'll pull the bands up, move the Fermi level near the valence band, and I'll start to accumulate holes in the valence band. So that's what my energy band diagrams look like. Carrier densities are then determined by the location of the Fermi level with respect to those levels, and we can simply relate those carrier densities to the surface potential. So we have our standard expression for carrier densities, but we remember that the bottom of the conduction band moves up and down when we change the potential with the gate voltage. So I can just express the carrier densities in terms of the surface potential that way. And if I pull the surface potential out into a separate term, you can see that the carrier density is what it was when the semiconductor potential was zero, multiplied by an exponential factor. So the electron density is what it was when the potential was zero, and then it increases exponentially when the semiconductor potential increases. The hole density is what it was when the semiconductor potential was zero, and then it increases exponentially when the surface potential goes negative. Now I'm just assuming that only one subband is occupied. If more subbands are occupied, I just add up all of the subbands here, and I get the same overall result at the end. Okay, so now we can ask, what is the charge as a function of surface potential for this device? Well, we didn't dope it, so there's no depletion charge. We have positively charged holes, and we have negatively charged electrons, and if we arrange things with work functions properly, then when we have zero potential, we have zero charge. In general, we'll induce some extra charge, because when the surface potential goes positive or negative, the electron or hole densities increase or decrease. So the net result is that we can write The charge in the semiconductors in this way, first term is due to holes, second term is due to electrons. If I'm talking about an N-channel MOSFET, then I am interested in the electron charge per square centimeter. So I'll just take the second term. It has a negative charge, and it's given by this e to the q surface potential over kT minus 1. So solving for the charge as a function of surface potential in this structure is even easier than it was in the bulk. And we can plot the result. If I've arranged things such that the Fermi level is right in the middle of the gap, then I get zero charge at zero potential. If I apply a negative potential, and I apply a big enough negative potential that I move the Fermi level down near the valence band, then I start inducing a positive charge due to holes. If I apply a big enough positive potential, I start inducing a negative charge due to electrons, and they build up exponentially. Remember what it looked like for the bulk. In the bulk case, we positioned the Fermi level near the valence band to begin with, so just a small negative voltage immediately caused holes to pile up. A positive potential first depleted the semiconductor, but I'm assuming that this is a very thin, undoped structure, so there is no depleted charge. And all we're seeing in the previous slide then was this red line part here, which is the inversion of electrons in the conduction band. So it looks similar, but not quite exactly the same. Okay, the next thing that we need to do is to relate that surface potential to the gate voltage. We now know how the surface potential affects the charge. How does the gate voltage affect the surface potential? Well, we do a little bit of electrostatics. The normal displacement field in the oxide is equal to minus the charge in the semiconductor. In this case, I have to divide by 2, because half of the charge images on the positive charge in the top plate, the other half of the charge images on the positive charge in the bottom plate. Due to the symmetry of this structure, we have a factor of 2 here. So we can compute the volt drop across the oxide. It's just the electric field in the oxide times the thickness in the oxide. And we get an expression that's very much like the one we had before, just a factor of 2, because only half of the charge images on the top plate. The gate voltage is the sum of the voltage drop across the oxide plus the potential in the semiconductor. So we get an expression that relates the surface potential to the gate voltage. Looks very much like the one we had before. We just have to be careful about the factor of 2. Okay. Now, if I look at this in subthreshold conditions, under subthreshold conditions, the amount of charge induced here is very small. So the first term in this expression is close to 0. And what that means is that the gate voltage is essentially the semiconductor potential. Remember, in the bulk, the semiconductor potential was the gate voltage divided by some parameter m. M is something close to 1. We'd like it to be as close to 1 as possible in a bulk MOSFET. Because of the way the electrostatics work in this extremely thin double gate structure, M is exactly 1. So we can directly control the surface potential with the gate voltage. Okay, so here's our expression that we developed for the charge as a function of surface potential. This is the expression for the inversion charge. And the gate voltage just follows the surface potential. So I can substitute the gate voltage in, and I have a simple expression that relates the inversion charge to the gate voltage, even simpler than it was in the bulk. Now, if we do a little bit of algebra, and I have some handout notes that explain how this all goes, that we can re-express this expression in terms of the threshold voltage. So once I pull the bands down so that the conduction band is near the Fermi level, I'll have an inversion layer. If I define a critical voltage called the threshold voltage in this manner, then I can introduce a term that we're going to call the quantum capacitance, and I can simply rewrite this equation in this form. So now the charge goes exponentially as gate voltage minus threshold voltage. And it starts to look like the similar one that we developed. Okay, so let's talk about this quantum capacitance just a little bit. So if we look at this subthreshold regime, what we've succeeded in doing is developing an expression for the charge under subthreshold conditions in this particular ETSOI structure. And we found that just as what happened in the bulk, that the charge varies exponentially with gate to source voltage. We compare that to what we had in the bulk, we see that they look similar, but this parameter M is not there. Now if we look above threshold, I'll just state the answer. Above threshold, in the bulk case, the charge was minus C inversion times VGS minus VT. Here we have two gate capacitors, one on the top and the one on the bottom. So if C inversion refers to the capacitance of one gate, then the total charge is 2 times C inversion. And again, C inversion is a little bit less than C oct, just as it was before. Okay. All right, now this quantum capacitance that we've pulled in, let me talk a little bit about what the quantum capacitance is. And it's easiest to do this at 0 Kelvin. So if I look at 0 Kelvin, the electron density is just the density of states, the number of states per square centimeter per electron volt, multiplied by the range in energies over which the states are occupied. So that's my expression at T equals 0. The conduction band is some constant energy minus Q times the potential. The semiconductor capacitance is the derivative of Q times the sheet carrier density with respect to the surface potential. You can see that that semiconductor capacitance is proportional to the density of states. That's what's known as the quantum capacitance. And in this case, you can see that it's easy to compute the semiconductor capacitance. It's just this quantum capacitance, and it's directly related to the densities of states. So knowing the oxide thickness and knowing the density of states of the semiconductor, we can compute the inversion level capacitance. It was much more difficult to do in the bulk, and let me explain why. In the bulk, we also need to compute the semiconductor capacitance. We have a potential well that's approximately triangular. We have an energy level that's a little bit above the bottom of the potential well that we compute self-consistently from the Schrödinger-Poisson equation. Now what we'll find is that when we do that numerical calculation is that the semiconductor capacitance is a little bit less, sometimes significantly less than the quantum capacitance. And why is that? Well, that occurs because when we increase the potential, we pull the bands down, that's the red line. That's just what happens in the extremely thin SOI structure. But we also make the well thinner because the electrostatics squeezes the potential well. The fact that we make it thinner pushes the first confined state up. So we don't get the increase in charge that we might have expected just by pulling the well down, because we pull it down and we squeeze it at the same time. So for a bulk structure, we really need to do fully self-consistent numerical calculations to get a handle on what that semiconductor capacitance is. Okay, so that occurs whenever the shape of the potential well changes with bias. Okay, so time to wrap up. What we've done in this lecture is we've developed an expression for the electron charge per square centimeter in subthreshold and above threshold. These expressions look very much like the expressions that we developed for the bulk MOSFET in subthreshold and above threshold. In both cases, the subthreshold charge goes exponentially with gate voltage, and the above threshold electron charge goes linearly with gate voltage. And we have the same question that we had in the bulk. Is there a single expression that works in both cases? And we have the same answer. Yes, there's a numerical one, or yes, there's an empirical one. Now, in the next lecture, we're going to switch gears for one lecture and talk about electrostatics in the other direction, two-dimensional electrostatics. And then we'll come back to this question in the last lecture of this week, where we revisit the empirical virtual source model and show how we can connect the subthreshold and above threshold with an empirical model. So we'll take that up in the last lecture this week.